In organic chemistry, making a precise alteration to a single atom without destroying the rest of the molecule requires extreme care. Take aldehydes and ketones. They share a nearly identical center, a carbon double bonded to an oxygen, known as a carbonyl group. But look closely at the adjoining branches. That slight difference in neighboring atoms means they require entirely different handling. You cannot rely on brute force chemical reactions here. If you drop a highly aggressive reagent into the mix, it will overreact, triggering a chain reaction that tears apart the entire molecular structure. To bypass these hazards, chemists use highly specific, ingenious chemical workarounds designed for surgical precision. In the lab, we call these named reactions. Mastering organic chemistry is about learning how to manipulate strict chemical constraints to your advantage. A text like this serves as the definitive field manual for executing those precise maneuvers. Let's say your objective is to carefully construct an aldehyde. One approach is to start with a compound called an acyl chloride and expose it to molecular hydrogen gas to gradually reduce it. This diagram shows the problem. Hydrogen is extremely reactive. It blows past the aldehyde phase, reacting until the molecule becomes an alcohol. Rosenmund added barium sulfate as a chemical poison, erecting a barrier that perfectly freezes the molecule in the aldehyde state. Alternatively, you can avoid the highly reactive acyl chloride altogether. The Stephan reduction takes an entirely different strategic route, starting with a simpler nitrile molecule and reacting it with tin chloride to safely arrive at the exact same aldehyde. Successful synthesis relies on recognizing the limits of your materials. Sometimes you have to intentionally cripple your own tools, and other times you need to abandon the path entirely and find a new starting point. This visualization shows our next objective, completely erasing the oxygen atom from the center of an aldehyde or ketone. We want that oxygen cleanly stripped away and replaced with two hydrogen bonds, leaving behind a stable hydrocarbon chain, known as an alkane. To achieve this, chemists often turn to the clemension reduction. It relies on a potent mixture of zinc amalgam and highly acidic hydrochloric acid to force the transformation. If your target molecule is acid-sensitive, the harsh clemension environment will rip it to shreds. Instead, you switch to the Wolff-Kishner reduction. This alternative track leads to the exact same alkane destination, but uses hydrazine in a fiercely basic, acid-free environment. True molecular control means possessing two distinct paths to the exact same destination. You choose your route solely based on the specific environmental survivability of your molecule. Let's look at a problem of chemical forensics. You have two identical glass test tubes. Both contain perfectly clear liquids. One is an aldehyde, the other is a ketone. How do you visually tell them apart? The solution lies in a behavioral difference. Aldehydes readily undergo oxidation, meaning they easily lose electrons when exposed to certain chemicals. Ketones stubbornly resist it. We can exploit this using the Tollen's test. By introducing a solution packed with silver ions into the mystery liquid, we are checking whether the sample is capable of being oxidized. The physical proof is immediate. If an aldehyde is present, it forces the silver ions to reduce into pure metallic silver. This creates a brilliant reflective mirror coating right on the inside of the glass. Fehling's test is a parallel diagnostic. It relies on similar oxidative logic to detect alpha-hydroxyketones, which secretly rearrange into testable aldehydes. Chemical detection relies on mapping these invisible behavioral differences. You probe the specific vulnerabilities of a molecule until it is forced to render a visible physical confession. When studying organic chemistry, long lists of named reactions can seem like arbitrary academic trivia. In practice, they serve as a hyper-specific menu of tactical maneuvers. Pioneers like Bernhard Tollens, Carl Wilhelm Rosenmund, and Erich Christian Clemenson mapped the exact boundaries of chemical reactivity. By documenting where brute force fails, they invented a permanent vocabulary for exerting precision control over matter. Understanding exactly where a reaction breaks down and knowing the exact workaround required to bypass that failure, this exact knowledge is what empowers modern scientists to engineer the complex pharmaceuticals and materials that sustain our entire world.